Let's continue looking at some of our basic functions. We've looked at the linear function and the quadratic function, which are the two vital ones. But then the next step would be our cubic. Now there's two different basic shapes of a cubic. The most common one we're used to is this one. And that's the one which has what we call a horizontal point of inflection. And inflection is the opposite to a reflection. Right? So reflect bounces back, whereas inflect, if you like, twists. Anything that can be factorized down to be a perfect cubic, so x minus a cubed might be times some constant, will have that classic shape. Otherwise, you're going to end up with a continuous curve with two turning points. So that up and down shape, of course, could be the flip of that. It also has a point of inflection. It's just not a horizontal one in this case. An inflection, by the way, is simply where it changes concavity. It goes from concave up to concave down, or vice versa. Just like we saw with the linear and the quadratics, every single cubic function can be made from either of these two shapes using translations, rotations, reflections, all those sorts of things. Recognizing our cubic function, and how do we recognize it? Well, there's our general ones. Again, each term has one pronumeral, but this time the highest power there, we see it as the power of 3. It doesn't have to have all the other ones, of course, but it must have power of 3 in there. Well, that leads on to polynomials in general then. Obviously, there's going to be lots of different shapes depending on the order of the polynomial. But let's talk about the perfect ones. Any polynomial that can be factored down to a perfect square, cube, quartic, pentic, whatever, will always take on the common basic shape. Now, if it's an even power, it will have the U shape. I'm purposely not calling it a parabola because only the x squared, only the quadratic is a parabola. The others are just U shapes. Our odd powers will have that inflecting shape, all of them. Now I've exaggerated it here, but what you find happens is as the power gets bigger, what you should see is it gets flatter at the base, and by geez, look at that odd one. I've really made that flat at the base, very exaggerated. But it will get flatter at the base and steeper at the sides. That's what will happen as the power goes up. Well, how do you recognize it? There's our polynomial. We'll end up doing a whole topic on polynomials and its different features later. But basically, each term does have one. We know the powers have to be positive integers, or 0, I suppose, technically, because the constant does have x to the power of something. It's just x to the power of 0. Whatever the highest power is, we call that the degree of the polynomial. So a quadratic is a polynomial of degree 2, a cubic polynomial of degree 3, and so on. Okay. So let's talk about sketching our polynomials in general. What do we look for? What helps us draw the curve? Well, the y-intercept, again, the constant number will always be the y-intercept. That's always very easy to find. Let's look at this one. Now, I don't have to expand it out to draw this thing. I can get the information. In fact, it helps if it's factorized, in all honesty. So if you can factorize the polynomial down into nice, neat factors, that can help. Because what I do know is the final constant number must be all of those constants multiplied together. Because when we expand out, that's the only thing that will produce a constant. So the first one we have 1, the next one will be -1 cubed, and the next one will be 2 squared. Well, that's -4, so I'll plot that in. X-intercepts are the roots. So we will solve the polynomial. Again, that's the advantage of having it in factored form. I can straight away see that, okay, the first one's going to produce -1, the next one's going to produce +1, and the third one will be -2. I've got that information. Out at the extremities, what happens out at the extremities? Out at negative infinity and plus infinity. A polynomial will always act like its leading term. Because you're dealing with such big numbers, and when you raise a number to a power, as that power gets bigger and bigger and bigger, the other terms start becoming irrelevant as far as the size of the thing is concerned. So you just look at the leading term, and that tells you what it will look like out at the extremities. So for this one, x times x cubed, x to the power of 4, times x squared is x to the power of 6. So I know that this is going to start and finish exactly the same as if I had drawn x to the power of 6, which is a basic curve. It has a U shape. It would start up here and it will finish over there. So I know that's what this curve is going to do. Now the roots. The roots will take on the characteristic of the factor itself if you were just drawing that. So if you've got an even powered root, at that point you're going to get a U shape. And the bigger the power, the flatter at the base, the steeper at the sides. So we have x plus 2 squared. Well, that's even. So I know at -2 I'm going to get a U shape. In fact, this one will look like a parabola. It's the power of 2. But in addition, I know because it starts up here, I know it must do something like that. It must be in that position. Well, the odd one, same deal. It's going to take on the characteristic of the factor itself. So it's going to have that inflecting shape. We've got x minus 1 cubed. So at +1, it's going to have that horizontal point of inflection. I know it finishes up there, so it's going to have that sort of shape. The other one here, -1, actually does also take on the characteristic of the root if you think about it, because it's the power of 1. It's a linear function. It will just cut through like a line, and that's what would happen at -1. That is our curve. Now, where it actually turns and things like that, once we deal with calculus, we can get a much more accurate picture of where it, well, this is a very accurate one because I used a graphing package that's precise. But if I was free drawing it, just a sketch, I'd just put them in roughly. It doesn't really matter. Do I know if it's on the left-hand side or the right-hand side of -4? Well, I don't. But I could sub in some numbers and check to see what's happening. But again, once we have calculus, we can find those points with a lot more accuracy of our picture. But for a rough sketch, we've got a feel for what this curve's looking like, what its picture is doing. Circles then. Let's move off from polynomials. Circles is another one of our very common pictures that we see, and that's a circle in case you didn't know. The general equation, x squared plus y squared is the radius squared. X squared plus y squared is the radius squared. Now with our circles, it is important the scale is the same on both axes. Otherwise your circle is not going to look like a circle, it's going to look like an ellipse. Circles, of course, are not functions. Remember, they are the composite of two semicircular functions, the top half and the bottom half, the positive square root, the negative square root. How do you recognize it from its equation? Well, there it is, x squared plus y squared equals r squared. I see, again, there's one pronumeral in each of the terms there. They're both to the power of 2. The other key thing with a circle is the coefficients are the same. Now the standard one, it's both 1, but if they were both 2, it'd still be a circle, like 2x squared plus 2y squared. If they were different, that's when you're going to get an ellipse. So x squared plus 2y squared would create an ellipse. If one was positive and one was negative, you don't get an ellipse, you don't get a circle, you will get a hyperbola. Correct. It's a hyperbola on its side. It's like the circle has exploded. So whilst it's positive, the circle is like this. As soon as one goes negative, it explodes the other way. The circle blows out and you actually get a hyperbola. What about functions involving square roots? Often ends up happening when your dependent variable is made the subject. So like the circle we were just talking about. So here we go. There it is. So we end up making y the subject, we've ended up with a square root. And of course we would have had plus or minus. And so here is the parabola on its side, which would be x equals y squared. Again, if we were to make y the subject, we end up with a square root situation. Positive square root's the top half, negative square root would be the bottom half. How do you recognise it? Well, if you're unsure, then square both sides. And then the basic shape will be revealed. So y equals the square root of r squared minus x squared. If you square that one out, you would end up, and you could reform it and get the circle that we recognise, and there's our parabola. Okay, remember, positive square root, top half, because you're dealing with the positives, negative square root, bottom half, because you're dealing with the negatives.